Thank you for having us today. My name is Annabelle Schilling. I'm a senior and I'm part of the Pingry School team.
Hi, I'm Alan. I'm also a senior.
I'm Evan. I'm a senior.
I'm Elvin. I'm a junior.
I'm Laura. I'm a senior.
It's my pleasure to present to you It Was the Age of Wisdom to Resolve the Coupled Crises of Homelessness and Housing Shortages. Homelessness manifests as the snarled face of human inequality and poverty. Consequently, it makes sense that we should take every action to better the quality of life for individuals living in these circumstances. Although Charles Darwin often wrote of homelessness with an air of awkwardness, unclear of what he could do about the matter, we intend to take more firm stances in pursuit of our spring of hope. Our global assumptions are that there will not be any major world events impacting cost of living or housing markets in the next 50 years, for instance, a global pandemic or a natural disaster. And then our second is that our recent data will reflect trends for the future.
Question 1. Create a model to predict housing units 10, 20, and 50 years in the future. So for this question, we had two assumptions. The first was that the growth of private building permits and the total housing supply will be adjustable by a multiplier. And the second was that there are no space considerations for housing in a city, so the total number of housing units is unbounded. So to start for this model, we plotted the provided M3 data for Albuquerque and Seattle in the two plots over here. Here we saw that there were too few data points to identify any clear trends. For instance, when we applied a line of best fit, we got relatively low R-squared values. So instead, we decided to search for alternative sources of data. While we were unable to find data on the number of housing units in both cities, we were able to find data on something very closely related, which is the number of private housing permits. And this data was readily supplied by the US Census Bureau. And the main advantage of this data was that there were many more data points, as we'll see on the next slide, and this allowed us to identify a very clear trend that we then used to train our model. So as we can see here, this is the housing permit data for Albuquerque and Seattle. This is monthly data from 1990 to 2024. However, across the entire time frame, we see that there isn't a super clear trend in the data. Instead, we saw that after the year 2010, there is a clear linear trend in both Albuquerque and Seattle, with R-squared values of 0.99 for both cities. And this trend can be explained by the financial crisis of 2008, which caused drastic changes in the housing market. And to avoid the ramifications of this crisis, we only use the post-2010 data to train our model.
So first, we did a linear regression on the cumulative sum of private housing permits against the number of months. Afterwards, we converted this number of housing permits into a number of housing units using a multiplier. Our multiplier is essentially a conversion rate for the number of housing units built per private housing permit. It is calculated by taking the change in the number of housing units as provided by M3 and dividing it by the change in the number of housing permits as in our monthly data set. Interestingly, we found that Albuquerque's multiplier was above 1. This indicates that there were more housing units built than private housing permits. This is probably due to the fact that there are types of housing, such as public housing, which do not require a private housing permit to be built. Here is a graph of our results. On the bottom left, we have our monthly training data in blue and the M3 provided data in green. In addition, the red line is our prediction. We predict that in Albuquerque, there will be approximately 140 new housing units per month, and in Seattle, approximately 500 new housing units. Here is a table of our predictions for 10, 20, and 50 years. We predict that in Albuquerque, there will be an approximately 30% increase in housing units in the next 50 years, and in Seattle, an approximately 80% increase. Here, additionally, we also performed a sensitivity analysis to test our model's robustness. To do this, we jittered our original data by 5%. Afterwards, we recomputed our predictions for 10, 20, and 50 years, and we found that using our monthly data was much more robust, as the mean absolute deviation was much lower compared to using just the M3 data. Finally, our model was strong because we were able to easily integrate more data, and in addition, our model is easily understandable, as the slope of the linear regression is simply the number of new housing units per month. On the other hand, our model has a few potential sources of error. In particular, we have to rely on using the number of housing permits, and we're also assuming that the linear trend will continue into the future. Finally, we are using 15 years of data to extrapolate to 50 years. This may not always be accurate.
Moving on to question 2, create a model to predict changes in the homeless population 10, 20, and 50 years in the future. So our assumptions, firstly, that the total homeless population follows a generally cyclic trend and will not rise to unreasonable levels, for instance, above 5% of the total population. The second being that the homeless population can be sorted into 3 categories: unsheltered, emergency sheltered, and transitionally sheltered. And then the third being that the underlying causes of homelessness have constant properties over time. So the justification for our model, as you can see with the graphs to my left, the overall homeless population data did not seem to follow any clear cyclical trend or pattern. However, the individual components, being unsheltered, transitional housing, and emergency sheltered, did. So we chose to analyze and predict these individual components and then sum them to predict the total homeless population. We also chose to truncate our data before 2011 to account for the 2008 financial crisis, and after 2019 to account for the COVID-19 pandemic. Our model was an ARIMA model, which means autoregressive integrated moving average. We use this because it's a time series model and our data was collected at regular intervals, that being annually. We also used this instead of simpler models, for instance, just linear regression, because it would be able to capture the more cyclical nature of our trends. We also used previous data points to forecast the future data. Our data was all stationary as determined by the Dickey-Fuller test, and the moving average means that we used a linear combination of our previous errors to represent our current error.
Okay, thanks, Annabelle. So now I'm going to talk a little bit about the different variables and equations that we use for our ARIMA model. So on the left here, we have a table with all of our variables, the most important of which you want to know are P, D, and Q at the top. So P represents the lag order, which kind of represents how many variables from the past you take in order to make a prediction for a certain time step. D represents the number of differences you take in order to make the data stationary, and finally Q represents the size of our moving average windows, which we take to kind of calculate the moving average errors as we go along. And on the, and also we determined all these values using an AutoArima model, which automatically performed Dickey-Fuller and ACF/PACF tests. So here we have our results for Albuquerque. So on the left, we have all of our graphs for our ARIMA model. So on the top left, top right, and bottom left, you'll see the 3 different components that Annabelle mentioned earlier. And together they sum to our plot on the bottom right, which is our total homeless population. And for each of the graphs, the blue line represents kind of the training data that we used, and the orange line is the predicted data using ARIMA. So we'll see that ARIMA is able to kind of accurately represent these cyclic trends and is able to capture these cycles in homelessness population in order to create the total homeless estimates that we see on the table on the right. So these are our results for Seattle, which are similarly structured. Again, we're able to see that we're able to represent these trends very accurately by using cycles. And again, we have our predictions on the right side. Finally, for some strengths and weaknesses of our model, our first strength is that we are able to account for cycles in the homelessness population. So we're able to kind of see when the homeless population is rising and falling, and we're able to account for that using our ARIMA model, which other models we tried weren't able to do. Secondly, we had a very robust model using our ensemble method. So we were able to combine predictions from 3 different sections to kind of form our ultimate prediction. And we also saw very clear trends within these 3 sections, which makes us confident that our prediction is accurate. Finally, we are able to estimate within reasonable bounds, which was not necessarily true for other methods we tried. For our weaknesses, our primary concern was that noise and error may be propagated into future predictions.
Question 3, determine a long-term plan to combat homelessness based on controllable and correlated factors. We make 2 assumptions for our third question. Firstly, we assume that the following 4 factors are correlated with homelessness, these being housing prices, CPI, which is a measure of the increase in inflation, the number of housing units, and the average inflation-adjusted income of the city. Our second assumption is that the trends in Seattle can be extrapolated to other U.S. cities. Our second assumption is because we selected Seattle as our target city. We did this because Seattle has much more available data than Albuquerque. Additionally, it's more representative of the nation because its poverty rate more closely resembles the US poverty rate than Albuquerque. We decided to use an ensemble method for our third model as well. This means using two different models. We have a correlation model, which is linear regressions to determine the direction of correlation for each of the 4 factors that we decided on. And then we have an importance model, which is a random forest to rank that importance. Now I will present the results of our correlation model. As you can see, we did linear regressions, and housing prices and CPI are both positively correlated with homelessness. This makes sense because as housing prices increase, houses are harder to afford, less people can afford them, more are homeless. CPI also makes sense because as inflation increases, it more negatively affects those who are impoverished and have less spending power. They are at more increased risk. 2 solutions would be to increase the amount of affordable housing around or to increase interest rates. However, some interesting results that we found were that housing units and inflation-adjusted median income were both positively correlated with homelessness, which seems like it shouldn't make sense. So we hypothesized that new housing units may not be affordable, which is why even though housing units are increased, more people are still unhoused. We also hypothesized that as income increases, the homeless population also increases because there's a wealth gap. So that means income at the top is increasing, but those at the bottom are still impoverished.
All right, next we have our importance model. So while the correlation model was able to tell us the direction of the trends for our 4 factors, the R-squared values for the lines of best fit were too similar. So we were unable to determine which factors were the most important, and this is where our importance model comes into play. So our goal here is to find the importance of the different factors, of the 4 different factors based on a random forest model. This random forest model was trained to predict the homelessness percentage based on the 4 factors as the input variables. And importantly, our goal here is to understand which factors are most important for influencing the size of the homeless population in the future. And to achieve that, we first predicted, can you go back, please? Sorry. To do that, we first predicted the values of both our input and output variables for the random forest model for the next 50 years. To achieve this prediction, we used the linear regression models seen in the previous 2 slides to predict housing prices, CPI, inflation-adjusted income, and total population size. And then we used our models previously developed from questions 1 and 2 to predict the number of housing units and the homeless population size. And then the last thing we did before training our model was to normalize our data by dividing the homeless population size by the total population size to get our output metric, which is homelessness percentage. And then finally, once we trained our random forest model on this data, it was able to output this metric called Gini importance for each factor. And then if we move on to the next slide, in this table, we can see these Gini importance results. And from this, we can conclude that housing prices are the most important factor for influencing the size of the homeless population in the future. Second to that, we have inflation-adjusted income, and then CPI closely followed by the number of housing units. So using our results from both the correlation and importance model, we proposed a 2-step plan of action to inform policymakers on how to combat the crisis of homelessness in both Seattle and similar cities across the US. So our first step is to increase the availability of affordable housing, and our second step is to reduce the wage gap. And then finally, for some strengths and weaknesses of this third model, the primary strength is that the importance model is very robust. External factors in the next 50 years, like any crises, they'll influence the values of our 4 input factors by a similar magnitude, meaning that the overall ranking order of their importance will be preserved. On the other hand, one weakness of our model is that the correlation model is not very robust. Because it's just a linear regression, it can't predict any outliers in the next 50 years, so it can't account for any crises like natural disasters.
Although for the large portion of this presentation, we've assumed that the past will determine the future, we hope to deviate from the trend of confused and complicit legislation that doesn't actually assist the homeless population, as characterized by the legislation of Charles Dickens' time. And so in an effort to conclude the winter of despair, we hope that you will consider the results from our models. And thank you very much for listening to our tale of 2 cities.
Great, thank you. I can start with a question. So I understand you use this like Gini importance in the last problem, and I understand it's a metric that comes out of the random forest model. Can you be a little bit more concrete about like what is that model and what is this actual Gini metric?
Yeah, so I guess I'll start with the Gini importance metric. So basically, within our random forest model, we're using our 4 input factors to predict homelessness percentage. And Gini importance measures how much each metric contributes to the accuracy of the model's prediction for homelessness percentage. So we're saying that the more a metric contributes to the accuracy of the model's predictions of homelessness percentage, the more important that factor is for influencing the homelessness percentage. And then that's how we derive our importance ranking.
Yeah, that makes sense. I guess maybe I'm asking for a more mathematical answer. Like I know what an importance metric is, but what is a metric is like some number that gets computed. So where does that number come from?
So the Gini importance is calculated from the gain in purity from each node in a decision tree. And decision trees you have multiple decision trees within a random forest. And the way the random forest works is the output from those decision trees are averaged to get your final random forest prediction. And then going back to those decision trees, they're a tree structure with a bunch of nodes, and each node is a decision. So for instance, one example of a decision could be, are housing prices greater than X or less than X? If it's greater, you go one direction to one output node. If it's less than X, you go another direction to another output node. And so at each node, you're examining a specific factor, and the Gini importance measures how much that node is able to correctly filter out the data. So how much that decision helps you get to your final prediction.
Okay, thanks. Part of the reason I'm asking is because you showed a nice plot which said like, I think it was housing units like correlated positively with homelessness, and you said both this one, exactly. Housing units and median income correlated positively with homelessness is a bit counterintuitive. And what I'm missing a bit is and you had explanations for this. Maybe it's because the income's increasing at the top level, maybe it's because there's new housing units but they're not affordable. What information does this random forest model have that would make it know that these are less important factors than, say, the amount of available housing?
So I guess what it boils down to is our R-squared, like we're looking, our overall objective is to see the correlation between our input factors and the size of the homeless population. And ideally, we'd like to get that information from these linear regressions, but because the R-squared values are all super similar, like 0.86, 0.85, and then it's super similar on the previous slide as well, they're so similar that we can't really deduce which one is more important, because small errors, which are obviously inevitable in our training data, can shift them just by a little bit and change that ranking order. So that's why we introduced our random forest model as a separate and more robust way to just determine which factors are more important than others by using a different measure of correlation to the size of the homeless population, which is that Gini importance metric.
Okay, thanks.
Can I ask a follow-up on this?
Yeah.
In terms of this relationship, did you look at time lags in terms of the impact of housing units and homelessness?
So basically, we did normalize by like population to get rid of the like time correlation, but we still saw that there was like positive correlations with very similar R-squared values. So for ease of like reporting and how intuitive it is, we just said it's the homeless population to these factors.
You have one?
Yeah. So in question 1, you looked at housing permits. Were you able to separate the types of permits? So for example, in my town, if I wanted to make any alterations to my house, I would need to get a permit, which is an existing house. Do you consider that not all housing permits are for new constructions?
We actually filtered our data based on private housing permits to build a new house, not for like any maintenance or construction.
Okay.
Yes, I do have a question. In part 2, from relatively short period of time, you censored 2 data points for very understandable reasons. There was economic crisis, and then we had global pandemic. So removing those 2 data points from, again, relatively short period of time, I do have 2 questions about that. We don't know what happens next, what kind of global event may happen. Are there any warranties, any guarantees that will not happen, and what that makes to your model. Like removing or versus what if those data points remain in the data.
Yeah, so we did use the data like before, I think 2011 and after 2019 to identify these cyclic trends. So we are confident that there are cyclic trends because we use that data to kind of see like, okay, it's going up and down here. However, we didn't consider it in our overall ARIMA model because we felt that it would skew our data. I think that in terms of planning for future kind of global events, we did assume that no significant global events would occur that would significantly alter the homeless population. But we do think that we could analyze like the COVID-19 pandemic and the 2008 financial crisis to kind of try to see how those crises affect homeless population and account for future crises by using those two examples.
Okay.
What were the periods of those cycles that you saw? And why do you think they're there?
Yeah, so wait, can you switch to like one of the future slides?
Yeah, one of the predictions. Maybe even.
Yes, so like over here, the periods did vary across the different components of homeless population. We saw that over here, they're roughly a couple years, and of course, like by city, they also varied. We did, however, see that for some of the components, I think like the cycles kind of averaged out over time. So we're hopeful that over time our policies will become more stable, and as such, they won't be as responsive to overall homeless population, because part of the reason we thought there were cycles were because we were analyzing kind of like policy changes and their effects on homeless population. And we saw that the reason there are cycles is partly due to the fact that policy kind of responds to homeless population. So when there's more of a crisis, policy kind of responds, kicks in to reduce that back to a normal level.
So you're saying these cycles here are based on cycles in homelessness, or is that what you're saying?
Yeah.
Why were there, do we have any sense of why there were cycles in the homelessness to start with?
Yeah, so that's kind of what I was saying before.
say it again.
But yeah, so we were thinking that policy is responsive to homeless population. So when homeless population reaches a certain critical level,
okay.
policy is
I
going to
get
kick
it.
into response. Yeah.
So it's just a feedback. Okay, yeah, sorry.
I have a follow-up question on this slide. So like you're training these ARIMA models based on the first part of the line, which is colored differently?
Yeah. So that's the blue part, which is the training data, which is like the data that we were provided, and then the orange is our ARIMA's prediction.
So like just in terms of sanity checking, like if we look at the bottom left plot, right? To me, that data looks like it's pretty much growing over time, but then the model predicts it flips back around and shrinks down to some level.
Yeah, so the reason we kind of took this model was because, for one, we saw that for the data we excluded, it was actually doing that. So it was actually trending into cycles. So we didn't want to just like fit a linear curve, even though we could have. And secondly, we also thought that, say for example, the top right graph, if we fit a linear curve to that, it would just go straight to like negative populations, which is not possible. So we thought there must be some reason that there are actually cycles, and it's kind of what I was talking about earlier, but we did see that also in the data.
Yeah, I mean, it makes sense as a justification. I worry, like, say you presented these plots to, I don't know, someone who is trying to make a decision based on this issue, I think they would have a hard time buying that, like, those trends would suddenly turn around and increase. Like, you could say, okay, the data told us that, but from, like, a sanity check perspective, you know what I mean? So, yeah.
Yeah, so I think that like given more time, we could try to account for the different crises that we remove data points because of. So say like the 2008 financial crisis and the COVID-19 pandemic. So say we were to include those points and scale them in order to kind of reduce the impact that the crises had on the populations, we would still see those cycles. So I think that given more time, we could try to implement something in order to include more data points and make our model more robust. Yeah.
Okay, great. Any last questions? Okay, thank you.
Thank you.
Thank you.